Welcome to my third video lecture for differential equations at the University of Guelph for this fall 2020 semester. And we are going to be going over uh, some solutions, but framed a little bit differently. We're going to be framing solutions in terms of what are called direction fields, which is like a graphical depiction of that idea from the last couple of videos. If you haven't watched them already, make sure you do. You'll want to make sure that you know what a solution is before we begin. But what we need here is to be able to represent the solutions to a differential equation, the general solution, which included that infinite number of solutions, in one picture at one time. And from that, we can think of, the solution to an initial value problem, an IVP, as one of the solutions from a whole collection of them. But drawing them is a little bit of a challenging task for students sometimes. It's the first topic that I think is a little bit more challenging for some people, but I promise that with some practice, it really comes together. So for this, make sure that you are right on top of those for you to try problems at the end of this section, and all of this, again, is available on our course link website. So sometimes, let's fill in these notes, ordinary differential equations, ODEs, are in a form that makes it easy to determine the qualitative behavior of solutions without actually having to do much work. Yeah, we went through this whole last section talking about solutions and solving, and one day we'll be solving, and that certain functions might satisfy these differential equations. But here we are saying, before we get to that, actually, let's see if we could actually draw these solutions, even if we don't know what the functions are that define them, which is kind of cool, actually, that you can know things about the qualitative behavior, whether a solution's increasing or decreasing, or what the curvature of the solutions are and all that stuff, without even knowing what the functions are that define those solutions. It's kind of cool. So we might be able to come up with some kind of graph of solutions without ever knowing the functions that define those solutions, or do both, right? What we're going to be working with in this section are, well, it's yet another category here. They're called autonomous equations. And autonomous equations are those equations that have a particular form, and that is, okay, for first order differential equations, dy by dt equals some function of y stuff, the dependent variable. These could be linear or nonlinear, okay? You might have like a y on the right-hand side. You could have a y cubed on the right-hand side, okay? And that goes back to the definitions that we talked about in the very first lecture, okay? What this says is essentially that the rate of change of y, like thinking of this in English, dy by dt, depends only on wherever the height is, right? It depends only on y itself. It's some function of y, okay? So, yeah, from there, let's talk about relating this to the material from the second video we talked about, where we mentioned this existence and uniqueness aspect, and that whole notion that if you have that existence and uniqueness, which exists in a lot of different frameworks, we only talked about a linear framework, but it does exist for particular nonlinear cases and stuff. But one governing thing for a lot of the graphs that we draw here is that for these first order differential equations, solutions can't cross. Okay, and this will help us when we draw a graph called a direction field. And I'm going to take us through a little bit of a derivation of kind of how this works, and we're going to do a couple of examples as well. Okay, a direction field is nothing more than a graph that tries to depict all possible behaviors, all solutions to a differential equation at once. And it plots the dependent variable versus the independent variable. So we'll draw in, right, there's an infinite number of solutions as we talked about, but we'll draw some representative ones to kind of show the different kinds of behaviors that can happen, okay? So when we're drawing graphs like these, there are a few things that are especially helpful to know. And one of them are those y values for which the dy by dt is equal to 0. This tells us where solutions have horizontal tangents. Okay, because that's literally from calculus the definition of a horizontal tangent, right? I'm just gonna right. These are all equations of dy by dt equals f of y. These are autonomous equations we're going to be working with. So at the start, okay, we're not solving, but I can look at this f of y on the right hand side and say, oh, wherever that's 0, dy by dt is equal to 0. And if dy by dt is equal to 0, that means I have a horizontal tangent from calculus. And moreover, since the equation's not going to change over time because nothing's right, like the f is dependent squarely on y, not t, right? It's always going to be dy by dt equals 0 for you know, that particular height or whatever. And so my solution is going to end up being an equilibrium solution, one that doesn't change, one that stays constant with all time. Okay. From a similar note, we can look for y values for which dy by dt is less than 0 or greater than 0, which tells us where solutions are decreasing or increasing with t. So if looking back to that dy by dt equals f of y again, wherever the f of y is greater than 0, okay, so for all those y values for which that function is greater than 0, I have that dy by dt is greater than 0. And that literally says the derivative of the solutions is positive there, right? So it's at those heights that I'm going to know that my solutions have to be increasing. And if the f of y is negative, that says dy by dt is a negative thing, the slope of the solutions is negative. And so you're going to have the solutions are decreasing, okay? Down here, this kind of speaks to what I had just said above, but an equilibrium value, oops, an equilibrium value for a differential equation is a value of y, think of it as a height, okay, such that if a solution starts at that height, at the initial t value, it stays there for all time. And as I said, when you have these autonomous equations where you don't have explicit dependence on t, the dependence dy by dt is only on like y terms and so on. If you start at a particular height where dy by dt is equal to 0, you're restricted to that height for all time. So for autonomous equations, you can always find equilibrium values by setting dy by dt to 0 and solving for y. And that's how we're often going to start these graphs. Okay, we're going to jump right into the first example. We have 2, and then I'm going to stop this video. But these will take a little bit of time to get through, and I want to be a bit careful. Okay, so we have a pretty simple differential equation. It looks like a linear differential equation, autonomous, so that we can kind of use these tools that we talked about. And it looks like it's dy by dt equals y minus 3. Or y prime of t equals y of t minus 3. Okay, we are going to draw a direction field for this, and all we're going to do is begin by finding equilibrium values. Differential equation is autonomous. I can set y prime to 0, so y prime equals 0 means the right-hand side is equal to 0. I get y minus, oh, I like to do the examples, calculations and stuff in red, so I'll be consistent with that. Y minus 3 is equal to 0, and that tells us that y equals 3 is an equilibrium solution. Right? You can see that, right? If I plug in y equals 3 up here, okay, I get 3 minus 3 no matter what, right? Y prime equals 0. So whenever the height is at 3, I have y prime equals 0, which means that I have a horizontal tangent. It doesn't matter what the t is, right? Wherever the height is 3, y prime is equal to 0. So I'm going to have horizontal tangent along y equals 3 for all time. Now, I'm going to see where this quantity is positive and where it's negative, because that's also going to help to kind of chart where the solutions are going to be decreasing and increasing. And we can see, right, if we have y prime of t equals y minus 3. So I'm going to just write that down right here. So it was y prime equals y minus 3. if y is greater than 3, it's easy to see, right? If y is greater than 3, then y is something like 4 or 5 or a million. And I get y prime is equal to that number minus 3. As long as y is bigger than 3, then y prime, the derivative of y with respect to t, is going to be positive. Okay? And hence, solution curves are increasing. So wherever the height of solutions is above 3, I'm going to have that the height is increasing. And for y less than 3, right, so just go back to the equation. Imagine plugging in 2. Imagine plugging in 1. Imagine plugging in 0. Imagine plugging in minus 500, right? If I have y prime equals 2 minus 3, 1 minus 3, 0 minus 3, minus 500 minus 3, I always get a negative number here. Right? It's really a matter of solving an inequality to figure out what, where this quantity is less than 0 or greater than 0 and so on. It's just that inequality is very simple here. But we have that solutions will be decreasing for all y less than 3. Okay. So we have a few pieces of information that's great so far, right? We have that y equals 3 is an equilibrium solution, okay? Once it starts there, it's going to stay there for all time. For y greater than 3, my solution curves are going to be going up. And for y less than 3, solutions are going to be going down. The question is, how do these curves, how do these solution curves curve, right? What is the curvature of these different lines? Lines, really, trajectories is how you want to think about that. So that's the word I used before. Okay. So right now, actually, before I go forward, I just kind of want to chart out what this looks like so far. So far, so I'm going to just put a little asterisk and say, so far, we have a picture that looks like this. Okay. Oftentimes, I would start a picture if I was doing something like this, and add to it as I go. I guess it's y equals 3. I'm going to keep the axis down here, and this is going to be t, and this is going to be y. So what we have so far is that y equals 3, so I'm going to call this 3 right here. It exists even before t equals 0, right? The solution exists in both directions here, but that's fine. I know that this here is going to be a constant solution. And you can see that the constant solution works in the differential equation. If I use y of t equals 3 and plug that in, I get the 3 minus 3 on the right-hand side. The derivative of a constant function 3 is 0, so I get 0 equals 0. That works out. That is going to be an equilibrium solution, as we talked about before. Okay. If I go above 3, I don't know exactly what the curves look like, but I do know that we said that for y above 3, solutions are positive in slope. So they're going to be going upwards somehow if I am above 3 to start. And for y below 3, solutions are going to be going downward. That's true even for like negative y values. So I want to make that a little bit clear here. Okay, so this is generally what the graph is going to look like, but I want to add more, some more accurate solution curves, I guess, in those fields where I've got the green arrows. And to get the curvature right, it's going to take a little bit of work, okay? There are a couple ways to do it, but I really like to do something a bit different than most textbooks go and kind of jump back to thinking about chain rule and thinking about concavity from first year, since you do graph sketching in first year. And so we have tools to talk about it that way. So yeah, curvature sounds a lot like concavity. And we know that concavity is related to the second derivative. The second derivative is, with respect to t, is d squared y by dt squared, okay? Remember, this is always a bit of a point of confusion, right? This is the differential equation. dy by dt equals some function of y. If I want to take the second derivative with respect to t, then I'm really taking the derivative with respect to t of this quantity. And that's not quite as straightforward as you might think at a glance, right? The second derivative with respect to t means I have to take the derivative with respect to t of the right-hand side, not y. D dt of f of y. And if you remember anything about chain rule, what this really says is that d squared y by dt squared is equal to, well, I have to take the derivative of f with respect to, with respect to the y, and then multiply by the derivative of what's inside, right? This is going to be df dy dt, right? I have to use chain rule to get to that derivative with respect to t. And I have to do that because the function on the right-hand side is not a function of t, it's a function of y, right? So taking that second derivative means that I have this product of different quantities here. And it's that product that helps tell us about what the curvature is. Okay, so this here, I want to make pretty clear, is the usual concavity that you're thinking about. D squared y by dt squared, that's the concavity. Okay, dy by dt, that sounds a whole lot like the slope of the function, right? df dy is whatever the derivative of the f is with respect to y. So when you go to find what the derivative of f with respect to y is, it doesn't directly tell you about the concavity of the function. It tells you about a relationship between the slope and the concavity. That sounds like a hard thing, okay? And yet it still boils down to something that's pretty straightforward. You just have to know how to interpret it, okay? So let's scroll down and see what I have to say about that, okay? Because it is a trap that students often fall into, right? If they want to find the curvature, they're like, oh, I just need the second derivative. I'm going to differentiate, I'm going to find df dy, and oh, where it's positive, it's concave up, and where it's negative, it's concave down. That's not true, because it's the concavity, that d squared y dt squared, that's what concave up and concave down are. It's, again, df dy is like a connector that describes the relationship between the slope and the concavity, okay? So let's go through this case by case. There are two, and it's honestly not that bad, but we have to think carefully. If df dy is negative, so this is question. This is going to connect these two things. Where this is negative, I want us to think about that for a second. If df dy is negative, then I basically have that the concavity on the left-hand side here and the slope over here must be opposite signs, okay? If I have, think about it, if I have a positive slope and I'm hitting it by a negative df dy, then I get negative concavity. So slope and concavity end up being opposite signs. If I have negative slope and I'm hitting it by negative df dy, I get minus times minus, which is positive for concavity. So the slope and concavity are opposite signs. Okay, that means that if the slope is positive, concavity is negative, or if the slope is negative, the concavity is positive. There are two pictures from your curve sketching from calculus that corresponds to. And these are those pictures right here. If we're increasing, we're also concave down, like this. Or if I'm decreasing, I'm concave up, opposite signs, like that, okay? These are the shapes that you can get if df dy is negative, okay? What do those look like? Well, I call it slowing growth or decline, right? If it's increasing at a less and less rate. If it's decreasing at a less and less rate. Essentially, think of this as like a hill that's getting easier to walk up, or you know, a hill that's getting easier to walk down if it's really steep to start, right? The slopes are getting milder. The growth or decline is slowing. The second case is if df dy, that connector between these two things, if that's positive, then the second and first derivatives must be the same sign, right? I'm going to go through those two examples too. Imagine if df dy is positive in that relationship up there, if the slope is positive too, I get positive times positive, which is positive. Slope and concavity are the same. If df dy is negative, if df dy is positive and the slope is negative, I get positive times negative, and I get negative for the concavity. So slope and concavity end up being the same in either case, right? So if that's true, that means if the slope is positive, so is the concavity. If the slope is negative, so is the concavity. And that corresponds to one of these two pictures. If I'm going up quicker and quicker, which is this. Or if I'm going down quicker and quicker. You get one of those two pictures, the other two, okay? So that's important, right? It's not concavity directly when you find df dy. It's this connector that tells you about whether you have slowing growth or decline or quickening growth and decline. You might have to rewind and watch through this explanation a couple of times. It trips people up, but it all depends on A, your understanding of chain rule, to first establish that relationship to begin with, and then also some concepts from graph sketching, okay? If you're having trouble with that, just talk to me. Reach out, post something in the comments, or send me an email. That's really, really important, okay? So, back to our example. We had, in this example, f of y equals y minus 3. That's a really, really simple f of y. And I can take the derivative df dy without any trouble at all. It's just going to be 1. Okay? So df dy is equal to 1. And 1 is a really simple positive number. That means that no matter where we are, it's always positive. And that means that I'm always in this second sort of case where I have quickening growth or decline. So that is what I'm going to be using when I construct my pictures, okay? We have quickening growth and decline for all y values. Wherever the graph is increasing, the graph is also concave up. Wherever the graph is decreasing, the graph is also concave down. So I'm going to put everything together here, and we will have our direction field. So we had y equals 3 was our equilibrium solution. That's roughly equilibrium-ish. This is our y-axis, this is t. Okay, and this is 3 right there. Okay, I'll put in those green arrows from before. We said that if we were above 3, the solutions were going to go upwards, and if we're below 3, solutions were going to be going downward. And now we know that the solutions are concave up here, right? I get quickening growth. So it's going to look like that, and maybe like that. Okay, always increasing, so there shouldn't be any little bobs there or anything like that. And remember that other thing, that none of these curves can cross. And that's important, right? If we didn't have a graph that looks quite like this, right? If I had the opposite curvature, I risk having these solutions like bump into this other line, and that's not possible, right? Right, this all kind of demonstrates the stuff from before, right? When we were below y equals 3, it was concave down with a quickening decline. And this kind of shows off what all of the solutions look like, right? So we have these things that kind of blossom upwards if we're above this equilibrium, and then dive downward if we're below the equilibrium. And none of these ever touch. They just grow infinitely close to, the axis as t gets very large negative. Oh, I can't get that close, but you get the picture. There's and the thing is, right, there's an infinite number of solutions here. I've drawn, what, 7 of them? But really, in between each one of those solutions, there's an infinite number more. And in between any 2 of those infinite number of solutions, there'll be an infinite number of solutions more. I used the analogy in one of my previous videos. Either I said it or I captioned it, right? This is the general solution to that differential equation. This is your plate of spaghetti. That's what it looks like when it shows up on your table, okay? if you have an initial condition that's attached to this, essentially it's picking out which one of these curves passes through that initial condition. So imagine you had an initial condition to make an IVP that gave the same differential equation, but then said y of 1 equals 3. Then I will want the particular solution that goes through the point 1 and 3, okay? And that's going to pick out one noodle out of this plate of spaghetti. So while the general solution to a differential equation can be thought of as a plate of spaghetti, the solution to an IVP is a single noodle from that plate of spaghetti. That's a super important concept going forward. I'm just going to highlight here that this 3, that was our equilibrium solution, and it should be right here, right? It's the one that stays there forever, okay? Some terminology here that will be important for some of your other courses is with regards to that equilibrium value, y equals 3 here is called unstable because nearby solution trajectories are repelled from it as time goes forward, okay? The idea is that if you step off of 3, even if you had a solution that was at a height of 3.1, that solution trajectory gets blown away from y equals 3 as time goes forward. That's true even if you're at 3.01 or 2.99999, right? You can be as close as you want to 3, but the solutions go away from 3 as time marches on. That makes an equilibrium point unstable, okay? An equilibrium point that attracts nearby solutions is called asymptotically stable, all right? So if we're going to find other equilibrium values that attract solutions, and that will be called an asymptotically stable equilibrium point. There's a bigger explanation of some other kinds of stability and stuff in the For You to Try, and so I urge you to explore those too. So yeah, what happens as t goes to infinity is generally an important notion. Here, if you take a look at what happens to solutions as t goes to infinity, right? We can see that solutions that start on 3, that's your equilibrium, will stay on 3 forever. So the limit as t goes to infinity would be 3 if our initial condition starts on 3. If our initial condition is greater than 3, the limiting behavior as t goes to infinity is infinite, right? The solutions will get blown off and up towards infinity. Whereas if the initial condition is below 3 to start, then eventually those solutions will tend towards minus infinity. I have one more example that I want to talk about before the end, just to kind of extend, and that will finish off this video. So we are going to draw a direction field for this slightly more complicated differential equation. We have dy by dt equals y squared minus 5y plus 6. You can see this in action, slightly more complicated dynamics here. So this is our f of y, okay? We can find a direction field by first finding equilibria and going forward. So let's do that first. So equilibria will satisfy if we set that dy by dt to 0, think horizontal tangent. So I'm going to write down here a 0 equals y squared minus 5y plus 6. I can solve this because this is a trinomial and I can factor it, right? So I get here 0 equals, looks like it's going to be y minus 2, y minus 3. And that means that y equals 2 and y equals 3 are equilibria. I'm going to draw those right into the graph right away. It won't be perfect, but I know that solutions, if they start on 2, will stay on 2 for all time. And if solutions start on 3, they'll stay on 3 for all time. I'm going to label this axis with, this is 3 right here. It's not to scale, but I kind of just want to demonstrate some stuff. This is my y-axis, this is t. Okay, I want to figure out what solutions are doing off of 2 and 3. So what do they do above 3? What do they do between 2 and 3? What do they do below 2? Okay. So let's keep working over here. Okay. And let's see here. If f of y is equal to y squared minus 5y plus 6, or f of y is equal to, as we factored it before, y minus 2, y minus 3. Where is that quantity greater than 0? Where is it less than 0? Well, that's not hard to do. This is, I'm going to write f of y as, just to be a little clear. Sorry, I'm just going to redo this bracket. Again, it comes down to solving inequalities, but f of y is going to be greater than 0 if both of these brackets are greater than 0, or if both of those brackets are less than 0, right? Negative times negative is positive. Positive times positive is positive. So f of y is going to be greater than 0 if y is greater than 3 or y is less than 2. If you need, you could write down a number line and like test points and stuff like that, because a lot of people will solve inequalities that way. Sometimes this one is probably simple enough that most people can eyeball it and see, oh, if y is bigger than 3, both of these brackets are going to be positive. If y is less than 2, both of those brackets are going to be negative. And in any case, it's for these values of y that solutions are increasing, because f of y is greater than 0 there. And I'm going to write f of y is less than 0 in between the two, right? Between 2 and 3, one is negative, one is positive. F of y is less than 0 if 2 is less than y is less than 3, okay? And solutions are going to be decreasing in there. So we have a graph now where solutions are going to be increasing up here somehow, increasing down here somehow. That is true even below the axis, so I'll try to draw my arrows accordingly. But in between the two, the solutions are going to be decreasing. Okay. We have one last thing to do, and it's that curvature thing. So I'm going to, you might have an idea of how it works, thinking that in most of these cases, the solutions aren't going to cross. And so drawing something in is probably not too hard to do, okay? But it's nice to justify it, and it's nice to be able to see that mathematically. So we have that f of y is equal to y squared minus 5y plus 6. And I'm going to take the derivative, right? df dy. And this is 2y minus 5. Okay. Again, from that big long-winded conversation last page, df dy is not describing the concavity itself, right? It tells us whether the solutions are going through quickening growth or decline or slowing growth or decline. So I want to see where this thing is positive or negative, and that's going to help me see that, right? So this here, you might be able to see, this is positive if, well, it looks like if y is bigger than 2.5, right? 5 halves. If y is bigger than 5 halves, and negative if y is less than 5 halves. I can see that that quantity is going to be like that, right? Plug in a value if you want. If you put in a 0 here, you'll see df dy is equal to negative 5, and so on. Okay? So I have that df dy is positive if y is greater than 5 halves. That corresponds to quickening growth or decline. Whereas where it's negative, that's slowing growth or decline. I'll remind you of what those pictures look like in case you need to remember. Quickening growth or decline means where it's growing faster. Where it's falling faster. Slowing growth and decline means the opposite, right? Where it's growing slower, and where it's falling slower. So it's these two pictures where y is less than 5 halves, and these two pictures where it's greater. So I'm going to draw in a little dotted line here to help me along, because that's going to be that breaking point at y equals 2.5 or y equals 5 halves. And it's above this, I'm going to get a different kind of set of pictures. Let's do this one zone at a time. Let's use the top zone to begin with. If my solution starts higher than 3, okay, I know that my solutions are increasing And I can see from my last work that I did that I get quickening growth and decline. So where I'm increasing faster and faster. Above here, my solutions must look like this. Okay, I'm going to go to the bottom. Okay. Oh no, you know what? I'm going to go into this region between 2.5 and 3. If my solution starts at like, say, 2.8 or 2.9, okay, I'm going to be decreasing because that's what I determined before, but I have quickening growth and decline because I'm greater than 5 halves. So my solutions are going to dive downward, 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 until I hit that dotted line, okay? And that's going to be true no matter where I start, even if it's back here, or even if it's up here, okay? These solutions will extend backwards as long as you like, but it's hard to draw because they're tightly packed together here, okay? Once they hit that line though, well, I'm now below 2.5, and I fall into that other category of curvature, where it's slowing growth and decline. So the pictures change, and the decline starts to slow. And that's good, because I don't want to hit that other line. And this is what solutions look like, okay? Again, they all continue onward, they just pack underneath each other and so on. There's an infinite number in there. Finally, below y equals 2, I know that my solutions are increasing again, but I'm in that second case here where I have slowing growth. So my solutions are going to be coming up, slowing, and not hitting that other line. And coming up, slowing, and not hitting that. Oops, it should always be growing, so I should be a little bit careful about that. But this is generally what my solutions look like. You could verify this using like graphing software and stuff. All right, let's see if there's anything left here before the end of this chapter. Yeah, so I think that's going to be it. Where we're going to be going next, however, is pretty exciting because we're finally going to put some quantitative solution methods to practice, right? We're going to be trying to find solutions in terms of functions for some basic kinds of differential equations, and things will scale up pretty quickly from there. So I appreciate you watching. There are some really technical things in this video, so I urge you to go back and rewatch and follow it right up by trying a couple of examples yourself. There are tons in there for you to try, and I hope that they are really helpful to you. All right? Thanks a lot, and I hope you'll tune into the next one.